This is Bardiya Aryanfard. This talk will be based on the paper Parameterized Complexity of List Coloring and Max Coloring by Dr. Fahad, Panolan, and I. We will first go through some problem definitions, and then we will gradually see the overview of the results. And then we will go through the idea of one of the proofs. The first problem that we have here is the list coloring problem. In this problem, which is an extension of the regular vertex coloring problem, for each vertex we will have a list, namely L of V, for that vertex, which represents the valid colors for that vertex. And so the question is that do we have any proper vertex coloring of that vertices such that every vertex has one of its valid colors? One of the parameterizations of this problem is the parameterization on the click modulator and the size of the click modulator. In this parameterization, we will have a subset D of the vertices, which we know that G minus D will be a click. So, in other words, if we remove that vertices from the graph, the remaining parts will be a click. And the problem is that given this click modulator, can we have a parameterized algorithm for list coloring where the parameter is the size of the click modulator? And the answer is yes. This problem is FPT. We know that from the paper by Gutin, Majumdar, Ordiniak, and Waldstrom from the year 2020. Another question that will naturally rise after answering to this problem is that what about extensions of the definition of click modulator? In other words, what will happen if after removing that subset D of the vertices, the remaining parts will consist of L clusters that are disjoint and do not have any edges in between them inside of the graph. Which brings us to the next problem, next parameterization, which is the list coloring L cluster modulator. In this problem, we will be given an L cluster modulator, and the parameter of the problem is K, the size of the L cluster modulator, plus L, the number of the clusters that will be remaining itself. Our first result is that this problem, not only it's W1 hard, but also it cannot be solved in time this. F of cardinality of D plus L times n to the power of small o of size of D plus L divided by its logarithm. For any computable function f, unless ETH fails, which it is widely believed that ETH will not fail. In order to solve this problem, we used a reduction from the subgraph, the colored subgraph isomorphism problem, which is known to not to be able to be solved in a time similar to this time complexity that we have here. This result has been given by Marx. So now let us build up the setup for the next problem that we will have, the max coloring problem, which all of the results that we have from now on will be different. Will be about different parameterizations of this problem. So now imagine that we have a graph G and the proper coloring lambda of the vertices of that graph, and this graph is also weighted, which means that its vertices have weights in natural numbers. So the first definition, if the weight is the weight of the color. The weight of the color is defined as the maximum of the weights of each one of the vertices which are inside of that color class. The second definition is the weight of a coloring lambda. The weight of a proper coloring lambda is the sum of the weight of all of its colors, which we defined the weights of each one of those colors just now. So the problem of max coloring is that given a graph G and an integer W and the weight function on the vertices, do we have a proper coloring lambda such that the weight of that coloring is at most W? The first parameterization of this problem that we will be talking about is the vertex cover. Our first result is that in the problem of max coloring parameterized by the size of its vertex color, we can find a kernel of 2 to k plus k vertices. The second parameterizations that we have is the problem of max coloring click modulator. In this problem, the max coloring is parameterized by the size of its click modulator, as we defined click modulator. So here we have that max coloring also admits a kernel, but this time the size of the kernel is 2 to k times k plus k number of vertices. So the last result that we will be talking about, and later we will review its proof idea, is max coloring 2 cluster modulator. In this problem, we have a subset D such that if we remove that subset of the vertices, then the remaining graph will consist of 2 disjoint clusters. And the results that we have about this problem is that this problem is FPT, but here we have a randomized algorithm for this problem, which runs in time k to the order of k times w times n to the power of order 1. And please note that although the previous problem is obviously a special case of this problem because one of the clusters might be empty, the other result is not implied by this result, since here the time complexity has the factor w inside of it, but in the previous result we don't have that. So let us now see a quick overview of the idea of this proof. In order to solve this problem, we use a reduction to the problem of a perfect colorful matching. In this problem, we will be given a bipartite graph G, which has its edges weighted and colored. And the question is that, do we have a perfect matching in this graph such that all of the colors has appeared at least once, and the sum of the weights of the selected edges are at most W. We know that this problem is FPT, and for that it is a more general case of this problem is proved in this paper by Banak et al. In the year 2020. They have used a reduction to the conjoining bipartite matching problem, which is also proved to be FPT in another work by Gutin et al. Using a randomized algorithm. And also we have independently proved this problem to be FPT using a direct randomized algorithm, which uses some algebraic tools which are kind of similar to the tools that have been used in the Gutin paper to prove that the problem of conjoining bipartite matching problem is FPT. So now let us see how we can prove this theorem. For that, first of all, we guess all of the color classes of the vertices inside of D, the two-cluster modulator itself. And by guessing, I mean that first we'll figure out how to solve this problem given that specific partitioning of that part of the graph, the two-cluster modulator part. And after finding how to solve that special case of the problem, we will use that as a subroutine to iterate through all of the different partitionings of the thing that we're guessing here, all of the different cases of the thing that we're guessing here, which here is the different color classes that D can have. So that is what we mean by guessing. And also, please note that once we know the color classes of the vertices inside of D, we can contract each one of these partitions into only one vertex, and approach this problem as if this two-cluster modulator that we have is a clique itself. In the sense that we know that all of these vertices will be having exactly one color, the same color, and no two of this partitioning will be sharing their colors. So we can assume that two of them are connected, so they do not share their colors. And also note that when we're doing this contraction, we should use the weight of the maximum weight vertex inside of this partition as the weight of the vertex that will be later representing that specific color class. So now, from now on, we will assume that the two-cluster modulator is a clique itself. So now, in the same manner, we will guess another thing. The thing that we will be guessing here is that we know that this vertices that we currently have inside of D can either share a color with a vertex in C1 or not, and also they can either share their color with a vertex inside of C2 or not. So they have 4 different cases regarding this. And these different cases are named here as A0, A1, A2, and A12, which we will call A12. In the case of A0, A0 is the part of the vertices inside of D which do not share their colors with any of the vertices inside of C1 and C2, so they are alone in their color classes. The second class is the vertices of A1, which they only share their colors with only one vertex inside of C1. Similarly, we have A2, the vertices that share their colors with only one vertex inside of C2. And then we have the class of A12, which is the vertices which share their colors with one vertex in A1 and one vertex in A2. So we will guess this part too in the same with the same meaning for guessing. So we will iterate through all of them later. So now the problem is reduced to that we need to solve that if this problem has a max coloring two-cluster modulator with weight at most W, given the color classes of D and A0, A1, A2, and A12. So now we will solve this problem using a reduction to the perfect colorful matching problem. So in order to do that from an instance G of the two cluster modulator max coloring problem, we will build an instance H of the perfect colorful matching. In order to do that, first of all, we need to get rid of A0. For the vertices of A0, we know that they are alone in their color classes. So we know that the weight that we will be having for those vertices color classes is their own weight. So we can reduce their weights. We can decrease the W by the weights of the vertices inside of A0 and totally remove them from the graph, since we have no limits on the number of colors that we're using. So now inside of D we only have A1, A2, and A12. So now we will get started to introduce H. In the graph H, each one of the vertices inside of G will be used in one of the partitions of H or in one of the colors of the edges. And the weight of the edges will be the weight of the color class that we will be having if we use its two endpoints and the vertex on its color on the same color class. So let's explain this more using this example. For example, here we have that the vertex V1 here is the vertex V1 from the C1 cluster, and vertex V2 is a vertex from the C2 cluster, and D4 is one of the vertices inside of A12. So the edge between between V1 and V2, which has color 4, will represent the idea of V1 and V2 sharing their colors with D4. And also note that the weight of such that color class will be 9, since the weight of all of its vertices are at most 9. V1 has the weight 9, D4 has the weight 7, and V2 has the weight 8. So the weight of this edge will be 9. So now let's get to the details of how H is constructed. In order to build H, we will have the vertices C1 and A2 on our first partition, H1, and then we will have the vertices C2 and A1 on the other partition. Note that A1 will share its color with the vertices of C1, and A2 will share its color with one of the vertices inside of C2. Therefore, it makes sense that they are on the opposite partitions of the graph H. And also, note that intuitively, it is kind of obvious to see that in an optimal case of the max coloring problem, at most one of the partitions C1 and C2 will be having the vertices which have their color classes only to themselves. In other words, only one of C1 and C2 can have vertices that they are the only vertex inside of their color classes. Because otherwise we will be having a vertex in C1 and a vertex in C2 that they are not sharing their colors with each other, and they are not connected, so they can share their colors. So we can merge those two color classes, and the result will be at most of weight of the previous coloring that we had. We will need to pad only one of the partitions of the graph H with more vertices, because only one of them which has more vertices inside of it will be needing to have vertices which are isolated, in the sense that they are not sharing their colors. Let me repeat the construction of H again. We will have C1, A2, C1 and A2 on one of the partitions, C2 and A1 in the other partition, and we will be padding the partition with the less number of vertices with some more vertices R. Now we can see that we will be only needing to we'll only need to add edges in one of the three cases, following cases. First case is the edges in between C1 and C2. These edges will represent the idea of the vertex from C1 and the vertex from C2 sharing their colors. They might be using also a vertex inside of A12 to share their colors with that too, but it might be not necessarily happening. So the color on these edges will be representing the vertex on the vertex inside of A12, and note that parallel edges are allowed here. And also, if we want to have the case that that vertices V1 and V2 from respectively C1 and C2, if those are not sharing their color with a vertex from A12, we will be using some totally different color, T plus 1 here. This is shown by T plus 1 here, which T is the number of vertices inside of A12. So the colors 1 to T represent vertices inside of A12, but T plus 1 is for the case that they are not sharing their colors with any of the vertices in A12. So that was the first case of the edges inside of the graph H. The other case is that one of the vertices of A1 or A2 is sharing its color. So it's either connected to a vertex from C1 or it's connected to one of the vertices from C2. So it's either from A2 to C2 or from A1 to C1. And note that no two vertices from A1 and A2 can share their color since they're inside of a clique. And the other case is from one of the vertices inside of two clusters to the padding vertices. So here it is also obvious that none of the vertices from A1 or A2 will be having edges to the padding vertices because of their definition that they're sharing their colors with cluster vertices. So now let us pay more attention to these examples that we have here to understand a little bit better. For example, here we have the vertex U with weight 2 inside of C1, and we have the vertex D6 inside of A1, which has the weight 6, and these two are not connected. These two does not have edges in between them. Therefore, they can share their colors. So inside of the graph H, we will be having an edge between U and that vertex D6 with color T plus 1, since it's not using any of the, it's not sharing its color with any of the vertices inside of A12, and its weight will be 6 because the maximum of the two weights, 2 and 6, is 6. Other than that, we had the other example that we talked about. For example, we have a vertex V1 in C1, a vertex V2 in C2, and we have another vertex D4 inside of A12, which is not connected to any of those vertices. So there will be an edge between V1 and V2 inside of H, where its color is 4, because we are using D4 here, and its weight is 9, because as I told, the maximum of these weights, 9, 7, and 8, is the 9 that V1 has. So this will be the high-level idea of how we will do this reduction. As you can see here, with a little bit going into the details, we can see that any of the perfect colorful matchings of the graph H with weight at most W will be equivalent to one of the colorings of this instance of max coloring 2 cluster modulator of the weight at most W, because as you can see, first of all of the vertices inside of the graph H will be having inside of the graph G will be having a color inside of the graph H, because first of all for the vertices of A2, C1, A1 and C2 they have an edge connected to them, which that edge will be representing the color the color class that those vertices will be having. And also for the vertices inside of A12, we also have a color for each one of them, because this is a perfect colorful matching. And as we told about the definition of this problem, all of the colors will be represented at least once. All of the colors will be appearing at least once inside of this coloring. So all of the vertices inside of A12 will be having a color too. And also it can be seen that we do not need to worry about the case that none of the vertices inside of T plus 1 will be chosen, because that will only happen when we have no vertices inside of A1 and A2, and also C1 and C2 have the same size. So in that case, we will be knowing that we do not have the color T plus 1, so we will not be adding that color at all. So now, obviously, this is not the only requirements that we need to check for not having T plus 1, but you can see that it is not hard to check that. And other than that, we can easily see that the weight on each one of these edges that represent our color classes inside of G will be exactly equal to that corresponding color class inside of G. So the sum of the weights of that matching in H will be exactly equal to sum of the weights to the weight of the coloring that we have inside of G. So that was the general idea and of the proof of Theorem 4. So in conclusion, we saw that the list coloring click modulator problem is known to be FPT, but we showed that this problem is W1 hard if it is parameterized by L cluster modulator, but it is still unknown that what is the complexity class when the list coloring problem is parameterized by the C cluster modulator with constant C greater than 1. So even for list coloring 2 cluster modulator, we still do not know the complexity class. The next thing that we had was that the problem of max coloring vertex cover will admit a 2 to k plus k kernel, but we still do not know whether it has a polynomial kernel or not. Next, we saw that the problem of max coloring click modulator also admits a kernel, but the size of that kernel is 2 to k times k plus k vertices. Also for this problem, we do not know whether or not this problem can admit a polynomial kernel. And at last, we had that the problem of max coloring 2 cluster modulator is FPT, but we used a reduction to the perfect colorful matching, which we only have randomized algorithms to solve that problem. Both the Banach et al. Algorithm and ours we're using randomized approach. So it can be an interesting problem to think about de-randomizing these algorithms. And also, the complexity class for more number of clusters is unknown for this problem too. We don't know what is the complexity class for parameterized number of clusters, and also we don't know the complexity class for constant numbers greater than 2 for the number of clusters that we have in the C cluster modulator problem of max coloring. So this is it, and thank you for your attention.